Hello everyone, in this video we will cover the section 6.2. In this section we show how to Laplace transform can be used to solve initial value problems for linear differential equations with constant coefficients. The usefulness of the Laplace transform for this purpose rests primarily on the fact that the transform of little f is related in a simple way to the transform of little f. The relationship is expressed in the following theorem. We suppose that little f is continuous and its derivative is piecewise continuous on any interval from 0 to any number. Namely, we consider positive values, non-negative values. Suppose further that there exist constants bigger k, a and bigger m such that we have this inequality for the function little f. For every value of t bigger than or equal to m, bigger m, then the Laplace transform of the first derivative of the function exists for every value of s bigger than little a, and moreover it is equal to s times the Laplace transform of f minus f of 0. Okay, we have a formula for the Laplace transform of the first derivative of the function little f. Okay, the Laplace transform of the first derivative of the function f is equal to s times the Laplace transform of little f minus f of 0. So using this one also we can find the Laplace transform of the second derivative by considering the function little f as the first derivative of this function. The Laplace transform of the second derivative is equal to, if we consider the function f as a variable for the Laplace transform here, so instead of little f we write its derivative, first derivative. Therefore we obtain the second derivative for this one, s times the Laplace transform of the first derivative. Instead of little f we consider its derivative minus the value of the first derivative at 0. And we have also a formula for the derivative written here. Therefore it is equal to s times the Laplace transform of little f minus f of 0 minus the first derivative of f at 0 s square, the Laplace transform of little f minus s times f0 minus the first derivative of f and from here we have a new formula. This is the formula for the second derivative of little f. It is equal to s squared times the Laplace transform of the function f minus s times f of 0 minus f prime of 0. Okay. Similarly, we can find the Laplace transform of the third derivative, fourth derivative, and so on. We can find a formula for the higher derivatives of the function f for its Laplace transform. Generally, by following this way, we obtain a formula for the Laplace transform of nth derivative of the function, and it is equal to s to the power n. You see, for the second derivative we have s squared here, so for the nth derivative we have s to the power n, s to the power n, s to the power n times lf minus s times f of 0 when we consider the s n minus 1 times the first f of 0, f of 0 minus s n minus 2, the first derivative of f at 0, blah blah, minus s times n minus 2 derivative at 0 minus f of n minus 1th derivative at the number 0. Okay, this is the general formula for the nth derivative of the function f for its Laplace transform. Using this formula we can solve linear differential equations with constant coefficients, for example. So use the Laplace transform to solve the initial value problem written here with initial conditions. The second derivative minus 4 minus first derivative, 4 times first derivative, plus 4y is equal to 0, and the value of the function y at 0 is equal to 1, and it's the value of the first derivative at the same point is equal to again 1. So how can we use the Laplace transform? So first we take the Laplace transform of the differential equation, considering the both sides of the equation, minus 4 times y prime plus 4 times y is equal to the Laplace transform of the number 0, which is equal to 0. And from here we have the linearity property for the Laplace transform. Therefore the left hand side of the equality will be the Laplace transform of the second derivative minus 4 times the Laplace transform of the first derivative plus 4 times the Laplace transform of y is equal to 0. And from here we use the formula written here for the Laplace transform of the derivatives of the function y. For the second derivative we have s times L f prime minus f prime of 0, or s squared times Lf, s squared times Ly minus s times y of 0 minus f prime of 0, namely minus y prime of 0. This term is corresponding to the Laplace transform of the second derivative of the function y from the formula. Minus 4 times the first derivative is equal to s times Lf, s times the Laplace transform of the variable y, minus f of 0 minus y of 0 plus 4 times the Laplace transform of the variable y is equal to 0. So by considering the coefficients of the Laplace transform of the variable y, this one and this one, so we have the Laplace transform of the variable y times s squared obtained from here, minus 4s plus 4. Minus, using the initial conditions, this one becomes minus s minus 1, so we have 1 here, minus 1, minus 4 becomes plus 4, is equal to 0, and from here the Laplace transform of the solution of the given differential equation will be equal to s minus 3 s minus 3 s minus 3 over s square minus 4s plus 4 plus 4. So if we take the inverse Laplace transform for this equality, we find directly the solution of the differential equation. Okay, namely the solution is equal to the inverse Laplace transform of the right hand side of this equality, s minus 3 s square minus 4s plus 4. And from here, namely to find the inverse Laplace transform of this rational function, we should make some simple algebra for this rational function to use a formula, because directly we don't have any formula for this function. Therefore, this statement should be converted into the statement that has a formula for its inverse Laplace transform. Therefore, we write s minus 3. So the denominator is actually s minus 2 to the power 2. And from here we have s minus 2 minus 1 over s minus 2 to the power 2. So from here we have 1 over s minus 2 minus 1 over s minus 2 to the power 2. So the solution is equal to the inverse Laplace transform, and we have the linearity property. Therefore, we can write separately the inverse Laplace transform of the first term, 1 minus s minus 2 minus the inverse Laplace transform of 1 over s minus 2 square. Okay. For the first one, we have a formula. If you remember, the Laplace transform of the exponential function e to the power at is equal to 1 over s minus a. Therefore, we write this is equal to e to the power 2 times t, because a is equal to 2. For the second one, we use a formula, if you remember from the previous section. The Laplace transform, the inverse Laplace transform of the function bigger f of c minus c, s minus c, is equal to e to the power c times t times the inverse Laplace transform of bigger f of s. So for bigger f of c minus s minus c, we have 1 over s minus 2 to the power 2, which means bigger f of s is equal to 1 over s squared, and c is equal to 2. C is equal to 2. So according to the formula, we write it is equal to minus e to the power 2 times t, e to the power 2 times t times the inverse Laplace transform of the function 1 over s square, and we have e to the power 2 times t minus the inverse Laplace transform of 1 over s square. If you remember, the Laplace transform of the power function t to the power n is equal to n factorial over s to the power n plus 1. Therefore, if you write 1 for n, we have 1 over s squared, and its inverse Laplace transform will be t. Therefore, we have exponential 2 times t times t. Okay, this is the solution of the differential equation. You see, directly we find the solution of the differential equation by using the Laplace transform. Therefore, you should know very well the formulas for the Laplace transform of some important functions and the properties of the Laplace transform. You see the answer here also. Another example, use the Laplace transform to solve the initial value problem. The fourth derivative of the variable y minus y is equal to 0, and we have the initial conditions here, you see. So first we need to see the Laplace transform formula for the fourth derivative. Using the general formula, that's right here, the general formula says that the Laplace transform of the nth derivative is equal to, namely, using this one, the fourth derivative of the function will be equal to s to the power 4 times the Laplace transform of f minus s cube f of 0 minus s square f prime of 0 minus s, the second derivative, minus the third derivative at the same point, okay, according to the formula. So using this one, so we obtain the fourth derivative is equal to this one, okay. And therefore, when we take the Laplace transform of the differential equation, you see we have the Laplace transform of the fourth derivative of the variable y minus y is equal to the Laplace transform of the number 0, which is equal to 0. This is equal to 0. And using the linearity property, we obtain the Laplace transform of the fourth derivative, which is equal to this term, okay, this term, minus the Laplace transform of the variable y. Using the initial conditions, y of 0 is equal to 1, y of 0 is equal to 1, the first derivative is 0, the second derivative is 1, the third derivative is 0. Therefore, the first derivative is 0, the second derivative is 1, third one is 0, and the value of the solution at the point 0 is equal to 1. So from here we obtain, first by considering the coefficients of the Laplace transform of the solution, so we obtain s to the power 4 minus 1 from here is equal to, here we have minus s cube, writing the other side we obtain plus s cube, and plus s obtained from this one. So s cube plus s over s to the power 4 minus 1 is equal to the Laplace transform of the solution of the given differential equation. So from here, s cube plus s is actually the multiplication of s and s square plus 1, and the denominator has the factors s square plus 1 and s square minus 1. Simplifying s square plus 1, so we obtain s over s square minus 1, s square minus 1. So from here we have L to the power, the Laplace transform of the solution of the differential equation is equal to s over a square minus 1. So to find the solution, we need to take the inverse Laplace transform of the right hand side, s over a square minus 1. So from here we have actually so we have again a rational function, and we don't have any directly a formula for this function. Therefore we will use partial fractions of this rational function. S over a square minus 1 is equal to actually s over s minus 1 s plus 1, and this one is equal to a over from here we have actually a over s minus 1 plus b over s plus 1. And to get the common denominator, we multiply this one by s plus 1, this one is multiplied by s minus 1, so we have s is equal to a plus a times s plus 1 plus b times s minus 1. To find the value of the number a, we write 1 to get rid of the second term. So when we write 1 for s, we get 1 is equal to a times 2, and the second term becomes 0. Therefore bigger a will be 1 over 2. And similarly, by writing minus 1 for s, we get minus 1 is equal to b times minus 2, b times minus 2, so we have b is equal to 1 over 2, 1 over 2. So we have for the solution of the differential equation, the inverse Laplace transform is actually equal to 1 over 2 over s minus 1, because s over s square minus 1 is equal to this addition, plus 1 over 2 s plus 1. Therefore, using the linearity property, we have 1 over 2 times the inverse Laplace transform of 1 over s minus 1 plus 1 over 2 the inverse Laplace transform of the function 1 over s plus 1. And we have a formula for them. Again, remembering the Laplace transform of the exponential function, so it is equal to 1 over s minus a. Therefore, we obtain the solution of the differential equation is 1 over 2 times exponential t plus 1 over 2 times exponential minus t. Okay, using the Laplace transform, we obtain directly exactly the solution of the differential equation. Okay, thank you very much.